This is week, what is this week? Week 6. So week 7 next week is our midterm exam. Also, your take-home is due, and we'll allot some time today. You guys had your take-home last week, and if you have questions on that, I can go over those questions, add to the clarity of that assignment. What we're going to do today is we'll finish up chapter 3, and I think we did most of the homework in class. Didn't we do most of the homework in class? So I think there was one that maybe, there was an integer one I think that I wanted to cover. Might have been number 35, it's accounting personnel one, so we'll cover that one. And then we'll move into chapter 4. Chapter 4, like I said, you're going to like probably the material we do later in this class better than the earlier material. This is kind of an odd mathematics class because we kind of start with the detail and then kind of back it out. So you'll see in chapter 4 we're still using linear programming, but we're using templates that already have that stuff built in. Okay, we're going to talk about network problems, and you'll see how that comes together. So let's first look at an integer one, and we'll also look at I think we set up one. I think we set up 34 on paper, but I don't think we did in Excel. Is that correct? The binary one? Yes. Okay. So let's look at 35 first, and then we'll move on back to 34. So this is on page 180 of your text. It says, Jones, Jimenez, and Sahota is expanding its tax services in the San Antonio area. The company wishes to be able to service at least 100 personal and 25 corporate accounts per week. They plan to hire 3 levels of employees: CPAs, experienced accountants without CPA, and also junior accountants. The following table gives the weekly salary level as well as the projection of the expected number of accounts that can be serviced weekly by each level of employee. They wish to staff its San Antonio office so that at least 2/3 of its employees will be either CPAs or experienced accountants. Determine the number of employees from each experience level the firm should hire for its San Antonio office to minimize its total weekly payroll. So let's take a look at this. This is known as a staffing model. So staffing models often have the additional constraint that some of the decision variables, or maybe all of the decision variables, have to be integers. So if we look at this first one, what are our decision variables? So let's start there. What are our decision variables with this first one? What are we trying to decide at JJS Accounting Services? Go ahead.
CPAs and experienced accountants and junior accountants.
Okay, so we have CPAs, we'll call them X1s, I guess. We have experienced accountants, we'll call those X2s. And we also have junior accountants, which we'll call X3s. Let me back out here. Okay, so those are our decision variables. What are we trying to optimize in this case? What are we trying to maximize or minimize in this case? We're trying to minimize, yes?
Salary.
Yeah, minimize weekly salary, okay? So it looks like CPAs are 1,200 X1. Experienced accountants are 900 X2, and it looks like junior accountants are 600 X3s. Okay, so we're trying to minimize that. Subject to, so we have, if this was the case, we would say hire no one. Subject to, we have some constraints though. For example, the company wishes to be able to service at least 100 personal accounts. So if I see 100 personal accounts at least, that means greater than or equal to 100. And it looks like the total number of, so how do I have to figure out these? The total number of accounts is 6. So the maximum number of corporate accounts is 3. How are we reading that? Is that, I don't know how the book interpreted that. Interpreted as 3 personal accounts for the CPAs, or is that 6 personal accounts? 3. So it's backing that out. Is that how interpreted? Okay. So it would be 3x1 plus, looks like 5x2 and it looks like 4x3. Okay, do you guys know what I'm saying there? It looks like what it did is said, okay, they can service 6 accounts, 3 at the max for the corporate, 1 at the max for the corporate, and 0 at the max for the corporate. So I just backed that out. Is that what you guys did? Is that, okay. Kind of an odd way to write it, but I think that's what the book wants us to do. And the corporate accounts, we have to service at least 25 of them. So our coefficients are 3x1 again, 1x2, and 0x3. Another constraint is all x1 are integer, right? We can't hire 1.5 CPAs. We either hire a full CPA or not a CPA. One other thing that I didn't cover is it wishes the staff at San Antonio office that at least 2/3 of all its employees will be either CPAs or experienced accountants. So I can do that a couple different ways. Okay, give me one way I can do that. One way I can encapsulate that constraint. What's one approach? There's 2 different approaches I could use. What's one approach? Sarah?
x1 plus x2 is greater than or equal to 75% of x1 plus x2 plus x3.
Okay, so very good. So one method Sarah says is and we'll do this method 1. So we will say the number of CPAs, which is x1, plus the number of experienced accounts, x2, has to be greater than or equal to, what did it say, 2/3? So we'll say 0.67 x1 plus x2 plus x3. Okay, that's what we're saying. The number of CPAs and junior accountants have to be greater than 67% of the total, right? The total x1, x2, x3. But we want to have a constant on the right-hand side. So what we should do algebraically is multiply this through. And then we need to subtract that from both sides. That gets us 0 on the right-hand side. But the left-hand side is a little bit uglier. It says 0.33x1 plus 0.33x2 minus 0.67x3 is greater than or equal to 0. Okay, this constraint will do it, right? Does that make sense? You guys see what we did there? Yes? Okay, so algebraically, even though that's not what exactly this looks like, that's what it does. Algebraically, it does what we want it to do. So that's option 1. That was method 1 to capture that summation constraint. Give me another way I could have done that. What's another way I could have done that? And it doesn't matter, either will work. Either will come up with the same answer. What's another way I could have captured that? Katie?
You could have made like a variable.
Okay, so I could have created another decision variable, and we'll say x4 is equal to the total, right? The total number of people we staff. But when I do that, I have to create that. I have to define it. And the way we do that is through a constraint that looks like this. x1 plus x2 plus x3 is equal to x4, or another way to write that, minus x4 is equal to 0. Okay, that defines x4, that creates x4. By forcing that to be true, which is what a constraint does, it forces x4 to be the combination of x1 plus x2 plus x3. Now we can use that. Now we could say x1 plus x2, that's our CPAs and our experienced accountants, have to be greater than or equal to 67% of x4, or minus 0.76 x4 is greater than or equal to 0. Okay, so either way, the combination of these 2 constraints or this one constraint will model that for us. Now, when we look at that, and I'm going to kind of cheat a little bit, I'm going to go to the like when you watch a cooking show and they go right to the baked cake. I'm going to kind of do that. So let's see if we look at this. If we go to material by chapter, you guys can't see. Material by chapter, chapter 3. And I go to, this one is 35. Okay, we see that they chose, when I say they, I mean the book publisher who did these, they chose to go the route of the one constraint without the summation variable. If I were to do it with a summation variable, I would have to add my summation variable up here. It would have to be a decision variable. And I think maybe I do have that. Maybe that's... No, I thought maybe that's what that was. So anyways, it is higher 2, 19, and 0. And if I look at my constraints, you see the only really thing that's additional because it's integer is that C4 through E4, there's a constraint that has to be integer, and they are 2, 19, and 0. Okay, so that will do that for me. The other one that I want to cover, and I think we did this in class, at least I think we did the constraints in class. We wrote those out, but we didn't look at the finished product, is let's look at 34 solution and make sure we understand where that came from. So this was a project selection model, and I told you that is a good application of binary values because so often we either do a project or we don't do a project, right? It's either on or it's off. We do it or we don't do it. So if you recall, we had 6 projects. Each project had a present net worth, like a net NPV value. We wanted to maximize that value. We only had so many programmers. We only had so much budget. We said 4 and 5 either have to be done together or not at all, right? They have to be equal, basically. So that's where it's x4 minus x5 is equal to 0. Project 2 only if project 1. So another way to say that is project 1 dominates project 2. So project 1 is greater than or equal to project 2. This is kind of the opposite way, but it just turned it, both sides. Not both project 3 and 6. So no more than one of those. That's what that is saying. X3 plus X6 has to be less than or equal to 1. And not more than 3 projects overall. So if you think about it, we have 2 to 6 combinations here, of projects we could do, right? That 2 to the 6 combinations. That's a lot of different permutations and combinations. It's hard for my mind to go through and say, these are the ones that work and these are the ones that don't. But it's easy for a solver to do that. And it comes up with a solution that says do project 1, project 2, and project 6. That gets me a net present value of 11.8. We used 58 of the 60 programmers. We used 3.3 of the $3.5 million budget. We do both. We do neither project 4 or 5, so we're okay. We do project 1 and 2, so we're okay. Project 3 and 6, we only do 1 of those, so we're fine. And we do 3 projects total. I think someone asked me this maybe last class, so I explained it. You might have a different value here. What is this saying? It's negative 1.1 E, negative 13. What is that saying? That is what? 0. Yeah, that is 0. It's scientific notation. It's saying it's negative 1.1 and shift the decimal place 13 places left, so it's like real small, right? It's very close to 0 because this thing goes through an iteration. And as it gets close enough, it stops. Okay, it stops where it's at. What you'll notice that you don't get, okay, which is why we kind of avoid using this when we do data, solver. You'll see C4 through H4 have to be binary. And when I solve this thing, I get a solution. And when I keep the sensitivity report, okay. A lot of these things, well, it's not so bad on this, but on an integer one, you're not going to get the detail you get on a regular sensitivity report. Okay, so it's a little more difficult to work with. So we try to avoid them, where we can. So that kind of finishes out chapter 3. Any questions chapters 1, 2, and 3. All right. Then let's move forward. Okay, let's move on to chapter 4. All right, and we're going to talk about a special class of models called network problems. Okay, and there's two types of network problems, well, multiple types, but two categories that we're going to talk about. We're going to talk about flow network models, where we're concerned with the flow of things from one area to the next. And we're going to talk about connectivity models, where we're concerned with connecting nodes in a certain way. So before we get into these models, let's introduce some things. So first off, okay, we're going to talk about nodes. And nodes are things on a network. They could be destinations. They could be computers if we're talking about a computer network. They could be cities. They could be a warehouse. They could be a company. They could be a factory. These are just general kind of things that can represent other things. They're like a destination. They hold some value. Between the nodes, there are something called arcs. Okay, arcs connect nodes. So arcs could be, roads. They could be pipes. They could be just functions like, hey, if I transport from here to here, it costs me this much. But there's some representation that connects the nodes together. We can have on the arcs, we can have functions. Okay, these functions mean, if we go from this node to this node, it's 6 miles, or it costs us $6, or the maximum bandwidth through that arc is 6. Okay, that it could be, many different things. So this is just generally speaking, some terms about network problems. Now, network problems are nice because there are business situations that lend themselves well to network formulation. A couple neat things about network problems. They're guaranteed, due to their unique formulation, they're guaranteed integer formulas or integer values that come back, which is a nice thing because of their special structures, mathematical structures. Network problems can be efficiently solved by compact algorithms due to this, right? So we are going to talk about some types of network problems, and you'll see that they're already set up for us inside of Excel. So the flow is the amount sent from one node I to j. So a lot of times we represent this, if we have a network problem like this, and let's say this is node 1, this is node 2, let's say this is node 3, and this is node 4. If we're talking about something being shipped from node 1 to 3, we represent it as x13, not x13, but x13. Like starts at 1, goes to 3. Okay. X24 would be, takes the arc from 2 to 4. Okay. So a lot of times we represent it that way. Sometimes there are constraints or upper bounds and lower bounds on these flows. So only so much can go through this pipeline or whatever it might be. We can have directed and undirected arcs. Generally speaking, when the flow is allowed in one direction, you'll see an arrow like this. If it's allowed in both directions, there's typically no arrows, but that's violated a lot of times in practice. If I'm talking about a network model, you'll see we're kind of shipping from supply nodes to demand nodes, and we usually don't use directed arcs. Some other terms, okay? Some other terms, these are kind of self-explanatory. Adjacent nodes, a node is adjacent to another node if an arc joins it. So 1 and 2 are adjacent, 1 and 3 are adjacent, 1 and 4 are not adjacent, right? 1 and 4 are not right next to each other. There's not a single arc that connects them. We have to go through a path, so we don't call those adjacent. We can talk about a path. It's a collection of arcs formed by a series of adjacent nodes. So let's go a little further. 6, 7 here. So 1, 2, 4, 5, and 6 is a path, right? That's a path through this network. 1, 3, 4, and 7 is another path through this network. Some certain connection. A cycle is a path starting a certain node and returning the same node without using any arc twice. So up here in this network that I've drawn, I only have one cycle. What is the cycle? There's only one cycle. What is the cycle? Right, very good. This is it, right? This is the only one where I can start this node, go out, come back, and never use an arc again. A tree is a series of nodes that contains no cycles. So this is now a tree, right? This is now a tree because there's no cycles in it, and this is also called a spanning tree because it's a tree that connects all the nodes in a network. If I had a network that looked like this, this would no longer be a spanning tree network because it's not all connected, right? So just some terminology that goes along with this. All right. So we're going to talk in this chapter, chapter 4. We understand what network models are, and we're going to introduce you to some. And they go by like types. And the two types are what we call flow models and connectivity models. So as the name implies, flow models are typically concerned with moving things, the flow of items from nodes to other nodes, like the flow of items on a network. Connectivity models are more concerned with connecting things on a network. For example, a connectivity model, if you imagine we start, there's one called the shortest path one, it's a connectivity model. If we start at 1 and we want to go to, if we want to go to 8, there's multiple ways to go from 1 to 8. Not really that many ways, but let's do this now. Yeah, there's multiple ways to go from 1 to 8. How do we connect 1 and 8? Is 1, 2, 4, 7, 6, 8 the best path? Is 1, 3, 4, 7, 6, 8 the best path? 1, 3, 4, 5, 6, 8. That's a connectivity model. We're trying to decide how to connect 1 to 8. The best way. That's a connectivity model. Flow models, like the first one we're going to introduce, are concerned with moving things, flow on a network from some place to another place. And these models are generic. They're general. So let's look at the first one. And the first one is called a transportation problem. And I'm sure we can all think of a need for this or a use for this in the business world. Transportation problems arise when we need a cost-effective way to ship items from origins that have limited supply to destinations that have demand for the goods. So give me some business place where we would use this, where we would need to ship items from one place to another that have supply and there's demand somewhere else. Okay, very good. So we have warehouses, where we have our products, and we need to get them to maybe 100 locations, right? So these are then my supply nodes, the warehouses, and all my retail locations are my demand nodes. Very good. From factories to warehouses. So anytime that I have items, we're shipping things, a transportation model can help us solve that. This is the general model. There are M sources, okay? M sources, these are supply nodes. So source, when you think about source, they have some supply. These are your warehouses. These are your manufacturing plants. Source I has supply. Source I has a supply capacity of SI. That's just generally speaking. There are N destination nodes. The demanded destination is D sub J. The objective always of a transportation problem is to minimize the total cost of shipping from those supply nodes to those demand nodes. We need to get product from here to there, and we need to do it the most cost-effective way. You know, usually time, or usually money, sometimes time, sometimes other things that we build. So I think what makes most sense is let's look at one of these. Okay, this is in your book, but we're going to kind of just summarize it and go through it there. So Carlton Pharmaceuticals supplies drugs and other medical supplies. It has 3 plants in Cleveland, Detroit, and Greensboro. These are my sources. These are my supply, the plants that make these pharmaceuticals. It has 4 distribution centers, warehouses, if you will, in Boston, Richmond, Atlanta, and St. Louis. Management of Carlton would like to ship cases of certain vaccine as economically and feasible as possible to these distribution centers. Someone has come up with this chart. Okay, they've said every item that we ship from Cleveland to Boston costs us about $35. If we ship from Cleveland to Richmond, $30, Cleveland to Atlanta, $40, so forth and so on. Each of Cleveland, Detroit, and Greensboro has 1,200, 1,000, and 800 units respectively, so a total of 3,000 units of supply. Boston needs 1,100 units, Richmond needs 400, Atlanta 750, and St. Louis 750. So we have demand of 3,000. So we have supply of 3,000, demand of 3,000. We need to get that from Cleveland, Detroit, and Greensboro to those 4 locations, and we need to get it there as cheaply as possible. Okay? We have to make some assumptions. Unit shipping costs are constant, which is kind of ridiculous. We know we violate that because you wouldn't say, well, we're shipping 1 unit from Cleveland to Boston. That's probably not, feasible. You're probably talking about, when you're doing something like this, you're maybe talking about pallets or something like that. So that's kind of a little bit ridiculous. All shipping occurs simultaneously. The only transportation considered between sources and destination. We don't have any intermediate points. Total supply equals total demand. So let's represent this as a network. And we have these 3 source nodes. We have these 4 demand nodes. We can ship from Cleveland, Detroit, or Greensboro to Boston. We can also ship from Cleveland, Detroit, or Greensboro to Richmond. We can also ship from those 3 sources to Atlanta, and we can also ship from those 3 sources to St. Louis. We also know that those arcs have function on them. So if we ship 1 unit or 1 pallet from Cleveland to Boston, it's going to be $35. 1 unit from Cleveland to Richmond, $30. So I want you to think about this once again in terms of a constrained optimization model. What are my decision variables? What am I trying to minimize or maximize? And what are my constraints? This is the problem. This is a transportation problem. It's a flow model of a network problem. Where would you start? What are your decision variables? So we started this out by saying we had 3 sources and 4 demand nodes. So, Devin?
How many units to ship from each source to each destination?
All right, so how many decision variables are you coming up with then, Devin?
12.
Very good. So my decision variables, okay, are going to be the number of source nodes times the number of demand nodes. Because if you think about it, every path is a decision. How many do we ship on this path? How many do we ship on this path? How many do we ship on this path, right? So every path is a decision. So I'm going to say X11 is how many to ship from Cleveland to Boston, comma X12 is how many from Cleveland to Richmond, X13 is how many from Cleveland to Atlanta, X14 how many from Cleveland to St. Louis. I would also have X21, these would represent the Detroits, X22, X23, X24, and also have X31, X32, X33, and X34. Okay, those would be my 12 decision variables. Good start. What am I trying to optimize? What am I trying to optimize? Okay, I want to minimize the total cost. And that's pretty easy, right? Those arcs are my coefficient. If I ship from Atlanta or Cleveland to Boston, it's $35, so it's 35x11 plus, it looks like 12 is 30, so 30x12. And I'd have all the way out to 28x34. All right, you guys follow me? Okay, so good. We have 2 of the 3 items done. We don't have to say they're integers because of the properties of these network models. You don't have to specify that. What are our constraints? Because right now our solution is don't ship anything, right? Because it's free then. Don't do anything and it's free. So what do our constraints look like here? So also I want to, so our decision variables are 12, 3 times 4. And the number of terms in our objective function are also 3 times 4. Okay. So what are we thinking constraint-wise? Okay, so one thing that we have to do is we have to fill demand. So at Boston, we need how much? 1,100. So let's do Boston first. We're saying equal 1,100. We have to get 1,100 at Boston. That makes sense, yes? It has to. They want 1,100. What's coming into Boston? Well, X11, X21, and X31. So X11 plus X21 plus X31, these are the things coming into Boston, have to equal 1,100. Does that make sense? I would need one for Richmond. I'm not going to do all these, but for Richmond, I would say, well, what's coming into Richmond? Well, X12 plus X22 plus X32 have to equal 400. So how many demand constraints would I have? In this case, I would have 4, right? So I'd have 2 other demand constraints. I'd have one for Atlanta, which is 750. You guys get the gist of how I write those. And I'd have one for St. Louis, which is 750, and you get the gist. So that's 4 constraints there. That's right. That's number 1. So what else? What else do I need? Okay, so as it's currently fabricated, it says 1,100, so it might try to ship, I don't know, it might try to ship 600 from Cleveland to Boston, and another 750 from Cleveland to Atlanta, and we can't do that, right? Because we only have limited supply at each of those nodes. So we need to capture that. So what goes out of Cleveland is 1,200, and we don't have to use it all. So we're just saying we can't go over the 1,200 that's there, right? So we're talking about less than or equal to 1,200. What's leaving Cleveland, love? So X11 plus X12 plus X13 plus X14. These are the things leaving Cleveland, right? Draw a circle around it. Those are the things leaving Cleveland. What's leaving Detroit? We have 1,000. So what's leaving Detroit is X21 plus X22 plus X23 plus X24. Has to be less than or equal to 1,000. And finally, we'd have one for Greensboro, which is 800. So we have 3 supply constraints. So 3, 4, 7. So every network problem is going to be this way, where we're going to have M times N, where M is the source and N is the demand, number of decision variables, 3 times 4 is 12. We'll have M times N terms in our coefficient, and we'll have M plus N, or 3 plus 4, number of constraints, right? So it all follows this same methodology, okay? And we can't ship negative, so we'd say all X greater than or equal to 0. This will do it. This will move product from our supply nodes to our demand nodes, and it will choose the most efficient route, guaranteed. Now that's a lot of work, isn't it? That's 12. We're talking about 12 decision variables. We're talking about 12 terms. I guess we could do it, right? We could set it up. We could do it. But what's nice about these things is all transportation models follow the same method. They're not unique. So if they're not unique, let's make one. Let's make a template, and then that's it, right? Then we just have to plug in our values, and that's what we've done. Now, one of the things about this one, and kind of go through here, you'll see the same deal that I put on the board. This is the supply, and these are the demand constraints. Now, what happened in this situation? What's my total supply? My total supply is what? I have how much total supply? Let's go back. Yeah, I have 3,000. And total demand is what? 3,000, okay. So the standard transportation model works fine when total supply is greater than or equal to total demand. And that's what we have here. 3,000 is equal to 3,000, so we're okay. What if I change this slightly and I said Cleveland only has 1,100? So that would mean total supply is 2,900 and total demand is 3,000. So what would happen if I tried to solve this model now? What would happen if I didn't know anything about linear programming and I used the same model and total supply is not greater than or equal to total demand? Total supply is 2,900 and demand is 3,000. What would happen?
To meet one of your demand constraints.
Okay. Right here, it's saying, hey, all these have to be equal, right? And we would change this to 1,100, and what's going to happen is we're not going to meet one of these. So what happens when you have something set up in Solver and it can't possibly meet it? What do you get? What message do you get? Not feasible, right? That's what we would get if we tried to do this. So fix it for me. So I would set this up with a standard template, and we're going to do that in a bit, and it would say not a feasible solution, so fix it for me. How would I fix it? Because now, all right, I'm using the standard model, but it doesn't work because I only have 2,900, my demand's 3,000. I know someone's not going to get 100, but I still want to use this model, so fix it for me. What could I do to fix this so it would work? Yes, sir.
You change the equal sign plus and
Very good. What I could do is I could change this to, less than or equal to, okay, which is good. But now the solution is still do nothing, right? Because, all right, great, I'll minimize cost, do nothing, so I don't ship anything. These are all less than or equal to. So how do I force out? How would I force out all the product? Because I know I'm not going to meet everything. How would I force it out? What would I change? So the supply nodes, you're right, are gonna be less than or equal to. What would I have to do to the demand nodes? Force it out. Very good. I would make those equal, and that would force it out. Anyone else have any ideas? How we could like not change the model, like the signs of the model, yet still use the model, knowing what we know, knowing we're smarter than it, knowing, what could we do?
Is
Yeah.
there a way to make a constraint to say that you have to?
Yeah, I guess you could, you could do that. Yeah, you could put another thing, you could leave it less than or equal to and force it out. That's still not what I want to do though. I want to try to, anyone else have an idea? Or if not, I'll just show you when we get to the thing. But
What if, like, are you talking like for like a neighborhood thing, like there's one location you know you want to fulfill on demand, so you usually
yeah. I'm thinking like I want to use this model. I don't want to change it. Like we changed it, right? We said, we had originally that this was, what do we have? This was less than or equal to, right? And these were equal to. And I want to use this model, but I know the way it's currently configured, it's going to say not feasible. So anyone have any ideas? Let's go ahead, Kate.
Make a total constraint thing like you did for the other ones?
Yeah, maybe I'll, you know what, let's put a pin in that, because I think if I show you what I'm going to show you, maybe it'll be clearer to you, okay? So here's what we're going to do. We're good, right? We're good. Let's solve this one, and here's what you're going to like. Let's go to Blackboard. And I want you to go to, under chapter 4, so material by chapter, go to chapter 4. And you're going to like this. It says network template. So click on network template. Okay. And it's a workbook that has multiple tabs. And if we look at those tabs, there are all the network models that we are going to, we're not going to look at all of them, but some of the network models that we're going to look at. And the first tab is a transportation model. So the next one is assignment, which we'll talk about next, transshipment, which we're not going to talk about, shortest path, and max flow, okay? So what we're going to do is we're going to use this template to solve that issue. So in column B, we're going to put in our supply nodes. So I think we had Cleveland. I'm just going to abbreviate Cleveland, Detroit, and Greensboro. And in column A, I'll put the associated supply they had. So 1,200, 1,000, and 800. And then the orange in row 2, we'll put the name of our demand nodes. So Boston, Atlanta, Richmond, and St. Louis. That's TL. And in row 1, we'll put the associated demand. So 1,100, 400, 750, and 750. Where these intersect, we're going to put the price. So from Cleveland to Boston, I don't know if you remember, it was 35. Let's see, this one's 37. This one's 40. This is kind of time consuming 30, 40, 15. Richmond is 40, 42, 20. And St. Louis is 32, 25, 28. So I put my supply nodes in column B and the associated supply in column A. I put my demand nodes in row 2 and their associated demand in row 1. And what you're going to like about this is if I go to Data Solver, you'll see everything is already set up for you. And the reason for that is because it is a transportation model. Every transportation model is basically the same. You're going to have m times n number of decision variables, m times n number of terms. You're going to have m plus n number of constraints. So we can build this, and someone built this for us, and we can use it, and it will solve our template. So let's solve our problem. So I'm going to click Solve. Don't need to change anything. It says Find the solution. Click OK. I don't know why it went to my other thing. But if we look down below, it comes up with my solution. And it says, your total cost is $84,000. And if anyone, some people might have you got something like that. That means your column's not wide enough, so widen your column. So it should be $84,000. And the way we're doing that is we're shipping from Cleveland, we're shipping $850 to Boston and $350 to Atlanta. From Detroit, we're shipping $250 to Boston and $750 to St. Louis. And from Greensboro, we're shipping $50 to Atlanta and $750 to Richmond. Now, as a manager, I might say, well, I don't like shipping 50 items. Maybe I take a look at that and say, well, that's fine. Maybe I don't want to do that, so I can reconfigure things, but because that's too small of a shipment, right? But that could be the case. And I could put constraints on that all these have to be at least greater than or equal to, well, let's do a couple things. But I could change that. Okay, so did you guys get that answer? No? You care? Yes?
Yep.
Okay. So let's go up here and let's make supply at Cleveland 1100. And let's resolve. And there is, could not find a feasible solution because as you guys indicated, right, what's happening is we're trying to satisfy all its demand, but we don't have enough supply to do so, so it says not feasible. So I could go into Solver and I could switch that to equal and that to less than or equal to, but I don't want to do that. So anyone have another idea? I don't want to change my model. I want to make it work though, right? So what could I do? Okay, sure. Someone's going to be short, right? We only have 2,900. We need 3,000, so someone's going to be short. Any ideas how we can use this model? Yes, sir.
Just subtract 100 from the most expensive route.
Okay, so make it 1,200 and do that? So make that back to 1,200 and then...
Just take 100 or however much you want to take off from...
So you're saying, like, if we put it back to 1,200, and we know that, I don't know what was the most expensive route, but maybe it was this one. Okay, 37, we can subtract 100. Anyone else have an idea how we can use this model?
Can we make a constraint somehow where demand is not greater than the supply?
Yes, we could. What we could do is, we could change this, right? We could change less than or equal to. We could change that, but any other ideas that I could just fake this out because I understand it? How about we make a fictitious supply area called Mecoville. And Mecoville luckily has 100 units, okay? And Mecoville, charges a lot of money to get that product out. Okay, so we'll say 100 everywhere from Mecoville. But now total supply equals total demand. And when I solve this, it should solve. It does. And what we see is 100 units got shipped from Mecoville to Richmond. It cost us 100 times 100, what is that, $10,000? But that's not real because Mecoville doesn't exist. So we have to tell Richmond, hey Richmond, you're only getting 650 because this is just something I made up, right? And the total solution is not 90,500. The total cost is what, 80,500. Does that make sense? Yes? So we still have a solution, we still use the model, but we know that we made up that Mecoville, right? We made up those 100 units to make it work. And that's not really going to happen in real life. Yes? That happens. Yes? Here's the other thing we could do. Well, another thing. Okay, so we want to use this model. Let's go back to where it was before. And we'll get rid of Mecoville. And we'll resolve it. And we're back to our 84,000. So the other thing is I want to use this standard model template, but it's shipping right now from Detroit to Boston. And for whatever reason, I don't know, there's something bad going on that line, or, I don't want to ship through that route. Usually it's Detroit to Boston is $37, but I really don't want to ship to that route. So I want to make sure that, I want to model what we call blocked route. Like, usually it's there, but today, let's say that's not really an option, right? But I want to use the same model that's 3x4, all those good things, but I don't want it to ship from Detroit to Boston. I don't want it to ship any items over that path. How can I model? There's a couple ways I could do this, but give me a way I could model a blocked route. What's one way I could do that? Give me one way I could do that.
Just make the cost really high.
Okay, very good. So what Devin suggests is if we make the cost on that route from Detroit to Boston, instead of 37, I don't know, let's make it 370. And if we resolve, okay, I hope it doesn't choose that route, and it doesn't. Why does it not choose that route, Devin? Because it is trying to optimize, pick the lowest cost. And I made it, because I didn't want it to ship over that, I made it cost prohibitive to do so, right? I said, if you choose that, it's gonna, so it won't choose it, right? Unless it's the last resort, and it wasn't the last resort. So I just made that went from 37 to 370, and it's not gonna ship across there because it's too damn expensive. Let's go back to 37, and I'm gonna resolve, and it's gonna ship across there. You guys know that. What's another way I could do that? Knowing what I know about Solver, because we didn't just start here, we started with the nitty-gritty. We understand the constraints, we understand the back end. We're not just using the model, we are understanding the model. What else could I do? I want to make sure something happens. How do I model that in a constrained optimization model? Very good. I can add a constraint to say, on top of the constraints that already exist, I can add a constraint that says, add a constraint that this, which in this case is C22, has to be less than or equal to 0. Constraint will force that to be less than or equal to 0. If I resolve it, it is now not shipping across that constraint across that path because I told it don't ship across that path. constraints force the model to apply. Okay? The third thing I could do, and in this situation I would not do it, is I could just remove that path from the model. I could say that's not a decision variable. That would be very difficult to do in the way this is configured because we're using arrays and ranges of data. So for our purpose, that's the only way. Those are the two ways to do it. Does that make sense? So using this is nice, right? So this is a nice use of this, but understanding what's happening behind the scenes makes you able to deal with situations that aren't your typical situation, right? Be able to adjust as a statistician. All right, it is 7:30, so let's take a 15-minute break, and we'll come back and we will continue down the network path. Okay, so we just looked into the transportation model and saw how we can move supply to demand. It's kind of relation model. It's also a flow model, something called the assignment problem. So the assignment problem is really a deviation or derivation of the transportation problem. And we all have this kind of situation, or we've had this kind of situation. We say, maybe we have 5 workers and we have 5 tasks, and maybe Jane is best at everything, right? But we can only assign Jane to one thing. So, and maybe John is bad at everything, but we have to assign John to something. So what's the best way to make those assignments, right? What's the best way to use Jane? What's the best way to minimize the damage John can do, okay? So you can do it when you're talking about, and generally speaking, we talk about assigning workers to jobs, but it doesn't necessarily have to be workers and jobs. You'll see in the example we're doing, we're assigning like a line, a production line, to an inspection line. So it's very similar to a transportation model. So M workers are to be assigned to M jobs. A unit cost or profit is associated with worker I performing job J. So we could be maximizing, some kind of profit or expected profit. We could be minimizing cost. And we're trying to minimize the total or maximize the profit of assigning a worker to a job. So I guess the best way to do this is to look at an example. This is Bulbs Electronics. They have 5 different electrical devices produced on 5 different production lines, and they need to be inspected. The travel time of finished goods to inspection areas depends on both the production line and the inspection area. So, we're producing items over here, 5 different assembly lines. We have inspection areas over here. Maybe this one's the closest, and that one's the furthest. So we need to assign a line to an inspection area, and there's multiple ways to do this. So that's one configuration of that. These are the worker nodes, and these are the job nodes. So these have to be matched, if you will. We have to, match these workers to these jobs in some way. And, someone came into our plant and they did a time study. They said, if you assign assembly line 1 to inspection area A, it's 10 minutes downtime. And if you assign assembly line 1 to B, that's 4 minutes downtime. So all those things, right? You can see the functions on the arcs, if you will. So what does this look like? Envision this, and we're not going to write this one all out because it's, like I said, kind of a derivation of the other one. What does this one look like? We have, 5 worker nodes and 5 job nodes. So what does the decision variables look like, or what is that going to look like? Thoughts? Yeah, we're going to have 25, right? We can assign 1 to A, 1 to B, 1 to C, 1 to D, 1 to E, right? All 25 combinations. And what's that look like, an assignment versus a no assignment? What does that call into mind, like I assign or I don't assign? Yeah, it's binary, right? So there's 25 things that can either be on or off, right? So that's the decision variables. If I make that assignment 1A, it's on, that costs me 10 total minutes. If I make 1B, it costs me 4 total minutes. If it's 3C, that's 12 total minutes. I'm going to minimize total time. That's going to be a big function with 25 terms in it, right? That makes sense? Yes? How does the constraint area differ here? How does the constraint area differ? Go ahead. Okay, you're right, there's 5 assembly lines, 5 inspection areas. How did, we had like, hey, it's total supply is greater than or equal to total demand. We can't ship out more supply. We have to equal demand. What does it look like in this situation though? In this special formulation where we're trying to match things? Yes?
So for each job, you have like it equals 1.
Very good. So for each job, A has to be assigned exactly 1 assembly line, right? So X1A plus X2A plus X3A plus X4A plus X5A, only one of those can be on, so it has to equal 1, right? So each job would have a constraint that says it has to equal 1. Also, what? Further, once I assign Jane or John, can't assign them anywhere else. So each worker would also have a constraint that I can only assign this to either A, B, C, D, or E. So if you think about it, really this comes out to, if you look at it, all this stuff going on, it's big and it becomes, basically a derivation of the transportation problem. This is just a version of it. With M equal 8 workers, there's going to be M factorial, which is 40,000 number of assignments. So this thing gets big pretty quick. You'll see, and we're not going to solve this one because it's kind of the same thing, but you'll see the transportation model. Well, right next to it is the assignment model, and you'll notice the assignment model is pretty much the transportation model with the areas where we put supply and the areas where we put demand are blank. Okay, so we use basically the same model. We could use the transportation model and just change all the supplies and all the demands to 1 and it'll still work, okay? It's the same logic. Does that make sense? Yes? Okay. All right, so those are 2 examples of flow models. Let's talk about one more final model in this section, and that is the shortest path model. I've got 2 versions of Blackboard here. And this is one that's kind of neat to think about because we don't have to think about it anymore. And I know I'm going to show my age when I talk about this. But we're going to talk about something called the shortest path model. Okay? The shortest path model is a connectivity model. It is how do we connect this node to this node through a path in the most efficient way. So for a given network, find the path of minimum distance, time, or cost from a starting point to a start node to a destination, the terminal node. So there are n nodes beginning with a start node 1 and a terminal node n. Bidirectional arcs connect nodes I and j, so it's non-negative distance, so you can go back and forth. Find the minimum path of total distance that connects the start node to the terminal node. So this is an example. We are trying to go from Seattle to El Paso, right? And we will say these arcs on these paths could be mileage, it could be minutes, it could be time, it could be, I don't know, maybe it could be costs. We could have any kind of function on those arcs, the thing that we're interested in, yes? Yes. And if you think about it, like I think back to my father, he'd plan our family vacations, right? This is how you used to do it. You get out the map, right? You take highlighter and you figure out this is how we're gonna go, day 1 and day 2. You know what I'm saying? And we could go scenic, or we could go, 4-lane highway, and we might start here, because there was all kind of options, right? And that was kind of, exciting to do. But now, what do? We just plug it in a GPS and say, all right, yeah, avoid toll routes, yeah, how long does it take, and you can do alternate routes. But this is happening behind the scenes, okay? So I want you to think about this as it pertains to a constrained optimization model. Once again, it is really behind the scenes, crazy enough, when you're using your GPS, it is using these kinds of solution techniques to say, hey, I want to go from Loretto to New York City. How do we get there? You know, it says processing, calculating route. It's doing this kind of stuff. So what about this? So I need to go from Seattle to El Paso. What do you think my decision variables are? What do you think? What have all my decision variables been so far in these network models? What's that? Okay, the arcs between the nodes, right? So x12 is a decision variable. x13 is a decision variable. x14, x34, x37, x46, x78. Because these are all possibilities, yes? These are all possibilities. I could take any of these, right? So those are all decisions. And think about it. They're either on or they're off. So it becomes binary, right? I either take that route or I don't take it. Yes? Yes. So that's good. Those are my decision variables. You probably can make sense of what I'm trying to optimize in this case. What am I trying to optimize? Minimize or maximize in this case? Yeah, minimize distance. So pretty simple. The coefficient would be 599 x12, 497 x14, 180 x13, right? 432 x34. That would be my objective function. Great. Right now, however, the solution is, because we have no constraints, the solution is don't go anywhere because you minimize total distance, right? Just staying, that's the solution. So how do I make sure I get from Seattle to El Paso? What are the constraints that make sure I get from Seattle to El Paso? This is where you really have to think about it. How do I make sure I get from Seattle to El Paso, constraint-wise? There? I like that. So Sarah's saying, I know I have to leave Seattle, right? And I know I have to arrive at El Paso. So let's start there, okay? Basically, we know we have to leave Seattle, so how do we make sure we leave Seattle? There's only, according to this, there's only 3 ways out of Seattle. Those are, it's x12, x13, x14. So x12 plus x13 plus x14 has to equal 1. We have to leave Seattle through one route, right? I don't know what it is, but we have to leave Seattle through one route, right? So there's a constraint for the start node. It says we have to leave it once. Make sense? Because if we go to Butte, we're never going to take Seattle to Boise. If we go to Boise, we're never going to go to Portland or Butte. And I like she said, it has to equal 1 for El Paso. So for El Paso, we have to enter it one time, right? Only one time. Because we're there, we're done. What's coming in El Paso? It looks like x1012 plus x1112 plus x912 also has to equal 1. Right? I have to enter it once. So we're leaving Seattle, we're forcing it to arrive at El Paso, but we haven't got there yet. So we need a constraint for the start node, we need a constraint for the terminal node, and guess what? We need a constraint for each node in the shortest path model. But what does that look like? So I'm telling you, we need a constraint for Boise, we need a constraint for Portland and Butte and Salt Lake City and Vegas and Bakersfield. What does that constraint look like? Well, like 4 people talking at once. It's crazy. Like that's like the most that's ever talked in this class. Who? Anyone? Huh? Who? God bless you. No. Like we got to think about. Okay, think about Boise. what about Boise? Either I go through Boise or I don't go through Boise, right? I either go through Salt Lake City or I don't. I either go through Vegas or I don't. So if I go through Salt Lake City, I got to make sure I what? Because I don't want to stay there. I leave it, right? And if I go through Vegas, I want to make sure I leave Vegas, right? So what does that look like? If I don't go through it, that's fine, but I don't have to leave it. So what does that look like? How do I make sure that if I go there, I leave it? Yeah, that's pretty much it. I would say the nodes arriving to Boise have to equal the nodes going out. So, like for example, let's do Boise. X14. What else comes into Boise? X34. There's only two ways in, and there's only one way out of Boise. Equals X46, or X14 plus X34 minus X46 has to equal to 0. So that's kind of what Nate said. He goes subtract it out. So if we what that does, it says if you come into an intermediate node, you have to exit that intermediate node, right? So that's the constraint. So this, believe it or not, by adhering to these constraints, it will force a path through the network that gets you from Seattle to El Paso and minimizes distance taken, right? So every node would have to have every node. So that's another reason why we don't do these ourselves. Because think about that. That would be one hell of a model we'd have to build, right? So now your GPS is doing that stuff for you. That's why, even with today's computers, even when it says calculating route, it's not like instantaneous, right? Because think about all the permutations going through. And when you say no toll roads, what do you think that is in terms of what the hell is it doing? What's no toll roads? In terms of what we're talking about. It's a constraint, right? You just put a constraint on that GPS, no toll roads, right? So it said, all right, I can't go through there, I can't go through there, I can't go through there. And that's why your options might be more limited, might take you longer, right? The same stuff. So this one's ugly. I'm not going to make you do any of these, but there is also a shortest path template, okay? And we put in all the nodes. We put in the from and the to. We put in the solution. And it'll solve it for us, but we're not going to. It's kind of. I don't know if you've ever heard the word kludgy. Kludgy means like it's not a good solution. Like it's not a good solution. It's kind of funky the way it works. I want you to understand this, but you don't have to use this. If you do want to use it for some purpose, you may. It's in the back of the chapter how we utilize that template. Okay. The other ones that are in here that we're not going to go through, so we're just kind of put a ribbon on chapter 4. There's something called a max flow model as well after the shortest path. That is more about dealing with it has a source and a sink, so it's about moving like liquid through pipes, or it could be not physical liquid, but it could be like bandwidth, like through a computer model. Like how do we get things from here to here, source to sink, when there's capacity involved. So it's another type of model. But what I'd like you to do, before we kind of end, what I wanted to do with our end here is let's. I know I got a couple questions via email about the take-home exam, so let's do that first. Let's look at that first. Not do it. We're not going to do it. But let's look at that first. And then let's talk about the in-class exam that's next week and what material is going to be on there, what the format of it's going to be like, all those good things. So, shoot, you guys fire away. What are the questions about the take-home exam? Sarah? Three, was that advertising one, Sarah?
Oh, that was the nurses.
Oh, yes, that should be integer, yes. That should be integer. That is a staffing model, yes, that's a staffing model. Kind of like the one we kind of talked about today, right? The CPA, 3-year common, that is an end to that, for sure. And to that end, they want at least 40% of its staff to be physicians. So that's a constraint. Okay? At least 40% of its staff to be physicians, that is a constraint. And that neither nurse practitioners nor physician assistants should account for more than 40% of the total staff. That's 2 constraints there, right? So there are like 3 summation constraints there. Does that make sense? So don't try to build this neither into one thing, the one constraint. It's actually 2. All right? I give another way you can do it, but that's good. What else?
Number 4, how there's like, the one that says this is one constraint, but it's like 2 in 1.
Which one's that? I'm sorry.
The,
And what part were you talking about, Lori, though? What part of this? Oh, this is 2 constraints, okay.
yeah.
All right, so this is, it's kind of a production mix and it's kind of a blending model, right? And we are saying that it has to have these certain specifications. So it's going to use summation variables. And we say it has to be at least 20% and no more than 30% rosé. So really that comes down to 2 constraints, because remember, everything is anded, right? It's all anded. It's the constraint, it's this has to be true and this has to be true. So it's 2 constraints. One that says, hey, it has to be greater than or equal to 20%. That's constraint 1. And the second constraint is the same damn thing, has to be less than or equal to 30%. You know what I'm saying? So it's actually, that's why I'm saying it's 2 constraints. Don't try to do that in 1 constraint. What other questions on this one? So let me just kind of give you an idea here. So one of the things you have to figure out for this one is, you're maximizing some profit contribution. And you can do that a couple ways. You could say, everything we sell this mixture for, what is it, $2.50 a gallon? So whatever we make is $2.50, and we'll call that like, I don't know, X4 minus whatever goes into it, which is, the cost for the wine, or $1 per gallon for the what. So minus $1 X1 minus $1.50 X2 minus 50 cents X3, something like that. You could do something like that. But the other way you could think about this is you mix all these things together. One thing costs $1, you mix that in. One thing costs $1.50, you mix that in. And one thing costs 50 cents, and you mix that in. And then when it all gets mixed together, it all becomes worth $2.50, right, per gallon. So going in, it's worth 50 cents a gallon, $1.50 a gallon, $1 a gallon. So try to think about, like, if I use 50 cents, if I use 5 gallons of this, okay, costs 50 cents going in, coming out, it's worth $2.50. So what's the contribution margin for that liquid? For $2, right? So every gallon of fruit juice I use makes $2. Every gallon of, I don't know what the hell this is, but makes $1. Every gallon of this makes $1.50. So that, sometimes I put that note there, and I think that throws people off. The other thing that throws people off on this one is these summation variables, these 50%, 30%, that all goes in the constraint area. Don't try to put that in the objective function line. And some people try to do that. They're like, multiplying the coefficient by 20, 30%. Don't do that. That's all just how we mix it together, so it's a constraint. Okay. And when I write things like interpret at least one of the shadow prices, that's when I'm looking for narrative for you to say, all right, I don't know, let's say white wine was binding, and we say that, for every additional gallon of white wine, between range of feasibility is 500 to 1,000, we get an extra $1.50 or whatever it is, okay? That's how I want you to interpret. So explain to me that you know what that means. Other questions? All right, so let's talk then about the in-class. All right, the in-class exam will consist of, and it's open book, open notes. So any resource that you want to bring, your laptop, your notes, your book, but no communication. So no, no texting anyone or Skyping or whatever. So no communication, right? So that's the only thing. Just you and whatever resource you want to bring. The peace poem, haikus, it doesn't matter. But there are 24 multiple choice. And they're worth 1.5 points each, so that's 36 points. And there's 4 problems, worth 6 points each, so that's 24 points. All right, so let's go through chapter by chapter. We'll talk about what's going to be on it. So, chapter 1 was kind of, if you remember, we talked about this concept of, modeling things. And what a constrained optimization model is. A lot of just kind of terminology in chapter 1. We didn't do much in chapter 1. And we talked about what constraints were, and we talked about what a model shell was. You remember model shell was that security one, that Sentinel security one, where we used variables instead of numbers. That was a model shell. Do you remember that? No? Sentinel security, it was like number 9 or something in chapter 1. 7 maybe. But that was a model shell, because remember it said things like, instead of saying we get $10,000 for this gig, we get B dollars. Do you remember that? And it says fixed expense are, instead of saying $1,000, it's Z dollars or something like that. That's a model shell where we build variables for numbers. Okay, chapter 2. So only, maybe 2 or 3 multiple choice from chapter 1. That's it. Chapter 1, really not a whole lot there. From chapter 2, that's really where we got into this concept of constrained optimization models, and we really started talking about, solving things. So, like terminology like what's the feasible region, right? We talked about the feasible region. Remember, the feasible region had interior points, boundary points, and extreme points. If a model has a solution, extreme point is always a solution. Do you remember that? When we have constraints can be binding or non-binding. What does binding mean? If a constraint is binding, what does that mean? Yeah, it's holding us back, right? It's using it all. And usually when it's binding, it also has with it a shadow price, right? I will actually give you, like a picture of a sensitivity report and ask you to tell me, interpret this sensitivity report, what's the range of feasibility? You don't have to say like, okay, read it and figure it out, right? And then there'll be 4 multiple choice, and you'll have to say what that is. I will give you like a situation, and I'll say, based on this situation, which of these constraints models that situation, right? So I'll have 4 constraints, and you'll have to say, well, of this situation that I wrote narrative, this constraint models that situation above. So, it's not going to be like definitions kind of stuff. It's kind of application stuff. There'll be a couple on there like with the constraints where they'll be binary, right? I'll give you a situation. I'll say which binary constraint models that situation. So that's a possibility. Understanding all those things that go along with sensitivity reports, like reduced cost and shadow price and range of feasibility and range of optimality, understanding those things. That was probably the most complex thing we did in this first part. So, understanding that, being able to, interpret that and understand what it's saying, what it means, the solution is important. So chapters 2 and 3 kind of meld together because there was a lot there. We spent a lot of time in chapters 2 and 3. 1 was like half a class, if you remember, and 4 was half of today's class. So 2 and 3 are where it's at. And as far as 4 goes, there's not going to be any 4 problems, chapter 4 problems. I'll ask you about the types of models that there are, network models. We talked about connectivity versus flow, right? I'll ask you about a transportation problem, and how we talked about how we model block routes, and maybe 3 or 4 multiple choice from chapter 4, but not a lot there.
You said no problems with that.
No problems from chapter 4. Okay, now for the problems, I'll give you 5. And you choose 4. Okay? I know some of you guys are high need for achievement and maybe do 5, but I don't care. I'll grade the first 4. I'm not picking your best 4. There's no bonus points for doing 5 right. So pick 4. Okay? And tell me which 4 you pick by circling them. So 1 will be kind of a binary one, kind of like, what was it, number 34 we did? The Corvex Corp. We did that today, I think, in chapter 3. Yeah, where we have some projects we have to select from, a binary model. You guys remember that one? So what you'll do on this test is you're not going to solve it in Excel. You know how we've been writing it on the board, decision variables? That's what you'll do, right? You'll explain to me that, hey, I could model this, right? I'm testing that you could do it in Excel via the take-home, but I'm testing that you understand from like the situation to a mathematical model via this test. 1 will be just a production mix, with a summation variable, or you can use the other method, but something with a total percentage of the whole. One will be integer. That's going to be like a staffing model. Probably not as complex, but maybe something like, I think it was number 28 in chapter 3, Burger Boy. Do you remember that? We had to have this many people. So 1 will be an integer. I'll probably have a minimization diet problem where we mix things together, try to minimize costs. Like I guess the example I can think of is that Moo Town buffet, cow chow. Remember that one? That awful one. something similar to that. And we will have like an investment portfolio. So I can't remember the number on that one, but we did a couple, investment mixes. Like a guaranteed return and a expected return, and we want to take this money and invest it in a certain fashion. And you'll have the entire class period to do that. So I'm generally here. I think I'm moving with them there. But I let you guys start at 5:30 if you want to start at 5:30, but as long as someone who can't get here till 6:30 complains that I didn't do it at 10:30, that's not a worry about, right? 'Cause I'm building's there. But if you want to get here, like I'll be here, like I'm gonna be in my office, walk 210. You get here early, like 5:30 or so, and you want to start the exam. Like I said, it's open book, open notes. I have a fantastic office. You can check out my office. I like the best office on campus somehow. 5 windows, view of them all. 5 windows, it's unbelievable.
So it's 210.
Walk 210 upstairs in the corner. Don't have many people around me.
You think it's gonna take us to 10?
No, but I mean, it'll take you time. It'll take you more than an hour. It'll take you some time because it's not. I mean, the multiple choice are not like look up this word in the index and then find a definition and circle the right answer. It's not. It's like you have to. It's thinking. It's really applying. It's
Tricky ones.
I don't know what tricky, but it's not. They're not. It's not a matching. It's not a word jumble.
But if you start at 6:30 and you aren't done by 9:15, you might as well just turn it in.
That's a good way to look at it. All right. Well, have a great evening.
These students go pretty nurse practitioners,
It's neither. That's a constraint.
That's right. And then physician assistants aren't more than 40 either.
Right. So there's 2 less than reasonable.
I just want to make sure.
I just wanted to check that some of my, I think I'm already like 5. But I just wanted to make sure it was set up correctly.
I didn't really look at it. You're gonna print it.
Yeah, I'll print it. I don't have a printer right now.
Oh, you don't have a laptop right now.
Yeah, I don't know. School didn't want to give me one, I guess. I don't know. I mean, I graduated undergrad here. I took my laptop. And then I set up to bring back, and they said, well, it doesn't matter. So I said, I mean,
What do you use? Lab?
Oh, I mean, I just, I emailed it, so I figured,
I didn't look at it.
yeah, just, I figured